Alright everyone, it's Mr. Edie back with yet another video. Today we're going to talk about reaction mechanisms, our fifth topic in kinetics. And before I can do so, guys, I briefly want to review what we took away from collision theory, right? So collision theory discussed, right, that there are ultimately two stipulations in order for a chemical reaction to occur. One, the atoms or molecules colliding must have sufficient energy to do so. And two, that the atoms and molecules colliding must collide in the correct orientation. Okay, right? Their collision must be in the correct orientation. Now, when we're going into reaction mechanisms, we have always talked about the overall chemical reaction, right? So the overall chemical reaction, as you can see, is H2 gas is reacting with ICl gas to form HCl and I2 gas, respectively, right? Now, if you guys take a close look at what's actually occurring here, we have one molecule of H2 reacting and two molecules of ICl reacting. That's the overall reaction. That's actually extremely rare. It's very rare for three molecules to hit in just the orientation that's needed in order for a reaction to occur. So what actually happens is that this same chemical reaction will occur in a series of steps called a reaction mechanism. Okay. Now, a reaction mechanism is simply a series of individual chemical steps by which an overall chemical reaction occurs. So like I said, guys, three molecules reacting together to collide in the proper orientation all at the same time is extraordinarily rare. So what actually happens is that H2 will react with one ICl molecule. Okay. Now when that happens, we go from three molecules reacting down to two. Okay. That is the probability of that occurring is much, much greater. Okay. And then they'll produce HI plus HCl. Now that molecule of HI that's produced will react with the second molecule of ICl, producing our HCl plus our I2. So again, this chemical reaction really occurs in a series of two steps. That's a mechanism. Now, if we were to talk about mechanisms in terms of biology, massive amount more of chemical reactions. Glycolysis alone, which takes your sugar molecule, your glucose molecule, and what it does is it ultimately converts it into a molecule of pyruvate A, so it can enter the tricarboxylic acid cycle. If I'm remembering it correctly, it's about 8 to 10 chemical reactions to do it. That's how big a mechanism can be in a biological system. Like, again, 8 to 10 steps. In AP Chem, though, the longest reaction mechanisms we will look at will be about 3 mechanisms, okay? Or excuse me, 3 steps. So let's analyze this mechanism a bit further. So again, step 1, hydrogen gas reacts with ICl to form HI plus HCl. HI plus ICl is step 2. They react to form HCl and I2 gas. Okay, so each one of these steps, guys, is called an elementary reaction. Okay, which is simply each step in a mechanism. Now, an elementary step cannot be broken down into simpler steps. They occur as written. In other words, they are going to show what exactly is colliding in that chemical reaction. Okay, so they show exactly what collided. So if we're looking at our first mechanism, if we're looking at step 1 of this mechanism, we have H2 collided with ICl. That's the first collision. Then in the second reaction, we have HI reacting with the other molecule of ICl. Okay. An intermediate is going to be a substance that is produced, then consumed in the same mechanism. So guys, our intermediate in this chemical reaction is HI. Okay, so HI is being produced, And then in step 2, it is consumed. That's what it means to be a intermediate. So in this case, we're talking HI. Okay. Intermediates, guys, we're going to take a further in-depth look at them in terms of the energy diagram, what it means to be there, and then ultimately where or how an HI, or excuse me, the intermediate is represented in a rate law, and it turns out they're not represented at all. But we'll move on as we go. And then the elementary steps in the reaction should be able to add to the overall reaction. Okay, so guys, just like how we learned in Unit 4 when we were adding the half reactions of redox, you can add the elementary steps of a mechanism. And the mechanism should always add back to that overall reaction. So the first thing you're going to notice, right, is HI is our reaction intermediate. We already talked about that because it was produced, then it was consumed in step 2. Notice, because of that, guys, I can cancel out HI when I go to add these steps up, and watch what happens. After I cancel these two out, right, because it was an intermediate, I get back our overall mechanism. So we get hydrogen gas plus 2 molecules of ICl gas yields our HCl molecule, 2 of them. Don't forget to add them up because there's 1 HCl here, 1 HCl down here, plus our I2. So very easy there. Okay, guys. Again, the elementary steps of that mechanism should add to the overall chemical reaction. The intermediate, or intermediates plural, should cancel out. Okay. Let's continue and talk about a term called molecularity. Okay, so there are ultimately, when we're analyzing our elementary steps within a reaction mechanism, we could have a molecularity of unimolecular, which would just be one singular molecular atom. We could have bimolecular, which would involve 2. And then we can have termomolecular, which is extraordinarily rare. And obviously, if that's extraordinarily rare, it's unlikely to occur. So we're going to see the more common ones, obviously, are going to be unimolecular and bimolecular, because that's simply going to be, they have a stronger probability of a chemical reaction actually occurring. So when we're going through the rate laws here, guys, it's simply going to be reflective of our reactants, and we're going to write it, the rate law, with respect to how many of each reactant we have. So, for example, the rate of our first chemical equation here, which was A is decomposing to form the products, right, would be the rate is equal to the rate constant times the concentration of A. Very simple there. Okay. Our next rate is A plus A yields the products. So we're going to say, okay, well, the rate is going to be the rate constant K times the concentration of A squared. And now I'm squaring it because there are 2 reactants of A colliding. So that's why it's ultimately squared. Okay. Now, our next biomolecular reaction would be the rate is equal to the reaction constant K times the concentration of A times the concentration of B. Notice that I haven't raised them to any power because there's only one A, there's only one B. Now, guys, these are the most common types of elementary steps, right? You can have a unimolecular elementary step, or you can have a bimolecular elementary step. A unimolecular elementary step would have a molecularity of 1, and a bimolecular step would have a molecularity of 2. Very simple there. Now we're moving into a territory below where, like I said, termomolecular is rare. It's unlikely to happen. The probability is low for 3 molecules to collide at the same time, all with proper orientation. So they're rare. But nonetheless, we can express them with the rate law. So we can have the rate is equal to the reaction constant K times, and we have 1, 2, 3 A's, so we're going to raise the concentration of A to the third power. We could also represent a thermomolecular reaction with the rate constant K times the concentration of A squared, right? Because now there are two A's, times the concentration of B. Or it could be three different substances, which we could have the rate is equal to the concentration of A times the concentration of B, and finally times the concentration of C. Now that's how we would express the rate law for all of these elementary steps. Now something to keep in mind, folks, is that these rate laws are propositions, right? A rate law can only be determined via experiment. So again, these are proposals, okay? They're not necessary. They have not been proven because the only way to prove a rate law is through an experiment. So just keep that in mind. You have to prove this experimentally. Okay, these are proposals. If we continue on, our quick check says, what is the rate law for the elementary step? Chlorine reacting with carbon monoxide will form ClCO. Okay. Now, when we do this, guys, first thing we have to talk about is I think it's just outright easier to write the rate law before we try to find it as a choice. So we would say that the rate is equal to our rate constant, and we have a chlorine reacting with a carbon monoxide molecule. So I'm going to say chlorine times CO. I don't have to raise chlorine or carbon monoxide to any power because there's only one of each reacting. Notice I'm not including the products because we don't include products in a rate law. And then if that's the case, A and B don't have them together, so I'm not going to include those. C is about the products, so our answer must be D. And of course that matches what we wrote there. Now, again, guys, rate laws are proven experimentally. This is just a proposal based off of the elementary step. We actually need data to run through the numbers to determine whether chlorine's first order, whether carbon monoxide's first order, second order, or zero order, etc., etc., etc. Okay? Now, the rate determining step. The rate determining step is the slowest step in a reaction mechanism, and it determines the overall rate of your mechanism. The rate law is written with respect to this slow step. And the analogy I like to use, guys, about the rate determining step is imagine that we're traveling on a 5-lane highway. And then at one point in the highway, there's construction, right? And we go from 5 lanes down to 1. Okay? That idea of going from 5 lanes down to 1 lane, okay, means that obviously if we were going 80 miles before, we're probably going 15 miles at the most now that we're done to 1 lane, right? Well, that construction on the highway has determined the average speed in which we're going to do in this trip. Doesn't matter how fast we're going beforehand. It doesn't matter how fast we're going after. The fact that we had to come down to 15 miles an hour because construction caused a 5-lane highway to go down to 1, that means our average speed of that trip is determined by the 1 lane. Similar to a chemical reaction, the rate determining step, which is the slowest step in that mechanism, determines the overall rate. You can't go faster than your slowest person, right? So that's what's happening here with the rate determining step. So if we're going to consider the overall reaction, nitrogen dioxide reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide, we would expect the rate law to be rate equals the rate constant times the concentration of NO2 times the concentration of CO. But again, we just got done talking that we need to look at the entire mechanism, not just the overall reaction. So the actual mechanism is 2 molecules of nitrogen dioxide react to form nitrogen trioxide, plus nitrogen monoxide. And as you guys can see, we're being indicated that this is the slow step. Now, in step 2, we have nitrogen trioxide reacting with carbon monoxide to get our NO2 plus CO2. A couple things before we write the new rate law. I just want to point out that an intermediate has been produced. NO3, right, is our intermediate because it was produced, then consumed in the mechanism. So NO3 is the intermediate here, okay? And then the next thing I want to point out is if I go to add these chemical reactions together, I will get our overall chemical reaction at the top, right? So the intermediate will cancel out when I go to add these up. We then have 2 molecules of NO2. We have 1 molecule of NO2 cancel out with 1 molecule of NO2 over there. And now with that said, let me go add these up correctly. Okay, so when I do that, guys, we're going to have our single model of nitrogen dioxide gas reacting with carbon monoxide, and it will produce nitrogen monoxide plus CO2. So this proposed reaction mechanism does indeed add to the overall reaction as shown. And now, guys, we can express the rate law with the slow step in mind. So the rate law is going to be the rate is equal to the reaction constant K times 2 molecules of NO2. So I'm going to do NO2 with the concentration squared. Okay. Now that's how you would write a rate law of a reaction mechanism. You're writing it with respect to the slow step. I just wanted to show you through our analysis that nitrogen trioxide was indeed the mechanism, and then of course the mechanism itself, the elementary steps, added to the overall chemical equation. Okay, now again, this would all have to be proven experimentally, right? You'd have to get the data, you'd have to do the chemical reaction, gather the numbers, crunch some data to truly see that NO2 was indeed second order. Okay, and also, indeed, if this is the correct mechanism. Okay, let's continue. If we look at the big picture here, guys, this is an energy diagram for a two-step mechanism. Okay, and an energy diagram, as we've talked about in the previous section, shows you how much energy is required for a chemical reaction to occur, right? In other words, it kind of outlines the reaction pathway. So here to here, the energy of the reactants all the way up to this first hump where the transition state occurs is called the E-act, right? So this is the amount of energy required for this chemical reaction to occur. So as you guys can see, there is greater E-act for the first transition state. Then the reaction occurs, they release some energy, and then we go to here. Now, then in order for our second transition state to occur, we got to gather some more energy, and then our transition state, that's when the intermediate's going to react, it's going to occur again. And then we finally have the energy decrease, and we form the products over here. Now, as you guys can see, it takes much more energy for step 1 to occur. Okay, so it takes much more energy for us to surmount the first reaction barrier and achieve that first reaction state. Because of that, step 1 of this reaction mechanism is in fact the rate determining step. Look how much more energy you need to go when comparing it to the second hump. So in that case, if we're looking at an energy diagram, our energy diagram is indicating to us, guys, that the first step of this mechanism is indeed the rate determining step, where the second one is not. So we can use energy diagrams and we can compare the energy of activation between transition states to determine the rate determining step. So, in summary, the elementary steps in a mechanism must sum to the overall reaction. The rate law predicted by a mechanism must be consistent with the experimentally observed rate law. Intermediates are not written in a rate law. A valid mechanism is not a proven mechanism. Mechanisms can only be proven experimentally. So, again, this entire video you've been hearing me say, oh, this might work, but we have to also make sure we gather the data and prove the rate law experimentally or the reaction mechanism experimentally. So again, these are all propositions. The only true way to test it is to run the experiment, crunch the numbers, and get the data. Okay, so let's find out when the first step of a mechanism is, quote, fast. So our goal for this question is to, 1, write the overall reaction for the following mechanism, and then 2, to determine the valid rate law for the mechanism. Now, guys, what I'm going to do is, as you guys can see, that the first step is fast, the second step is slow, and then the third step of this reaction mechanism is fast yet again. Okay, before I decide to write the before I decide to write the overall chemical reaction, I do want to write the rate law first because, as you guys know, when we add these together, I'm going to be crossing things out. So it's just easier right now to write the rate law first. So we'll actually flip the steps here. First thing, guys, I want to point out is that we have a couple of reaction intermediates, which again are substances that are produced then consumed in the chemical reaction. So we would have a reaction intermediate in the form of N2O2. So we have a couple of intermediates again, so let's list them out. Again, an intermediate is a substance that's being produced and then consumed. So we have N2O2 is our first one. Okay, and then we have a second intermediate in N2O. So here it is, it's being produced, and then it's being consumed in this step. So we have 2 reaction intermediates. Okay, now we just got done talking about how rate laws are written with respect to the slow step, right? So if that's the case, I should be able to write, well, that the rate is equal to the reaction constant K times the concentration of H2 times the concentration of N2O2. And here, folks, we have run into our first snag, okay? As you know, I can't represent a reaction intermediate in my rate law, so I have to do something called the pre-equilibrium approximation. Now, there is one minor thing that I do have to correct here, guys, is before we can do the pre-equilibrium approximation, is for our rate law here that we wrote for our slow step, I really should have that label as K2, because in this mechanism, obviously it's the second step, okay? Now, the pre-equilibrium approximation, basically, guys, in short, what I'm about to do is I'm going to find a way to solve for the concentration of our intermediate and express it so it's no longer represented in the rate law. So again, in short, what the pre-equilibrium approximation does in terms of our rate law is it's going to allow me to express the concentration of N2O2 in the means of anything else that's not an intermediate in the chemical reaction. So what it does, guys, is when we see a double reaction error, right? So we see a chemical reaction that's possible to occur in the forward and reverse direction, right? So the step 1 here has a forward direction and it has a reverse direction. I can set the forward rate equal to the rate of the reverse. So we'll say that the rate of the forward for our equilibrium step, or step 1, is equal to the rate of the reverse. Now, because of that, I can express two different rate laws, right? So I could say K1 of the forward times our our concentration of NO squared is equal to K1 of the reverse times the concentration of N2O2. Now, I ultimately want to solve for N2O2, right? So I'm going to solve for N2O2 now by dividing by K1 of the reverse. So the concentration of N2O2 is K1 of the forward direction divided by K1 of the reverse times the concentration of NO squared. And now I can go plug this whole value in to NO2 in my actual rate law. So I'm going to take this whole value and I'm going to substitute it over here. Okay, so when I do that, we're going to get the rate law is equal to K2 times the concentration of H2 all over, or excuse me, times K1 of the forward divided by K1 of the reverse times the concentration of NO squared. Now, I'm going to just combine like terms here. So I'm going to take my constants, guys, and I'm going to multiply them together. So that's going to be K2 times K1 of the forward over K1 of the reverse times the concentration of H2 times the concentration of NO squared. Now, ultimately, because this stuff here is all just a constant, right? So if I multiply three constants together, I just get a new constant. So that can be simplified to just the rate constant. And our rate will be the rate is equal to the rate constant times the concentration of H2 times the concentration of NO squared. And that is our rate law for this chemical, or rather for this mechanism. And again, the reason why we had to do this was because the mechanism had N2O2 originally written because the second step was slow. We can't have intermediates expressed in a rate law. We need to finish the problem now, and to finish the problem, we have to add these up. So let's add them. Remember, reaction intermediates are not represented in the rate law, so I'll cancel those out. It looks like we're going to have 2NO gas reacts with 2H2 gas to produce 2 molecules of water plus 1 molecule of N2 gas. Just give it a quick make sure I added everything correctly. So 2 nitrogen, 2 nitrogen, 2 oxygen, 2 oxygen, 4 hydrogen, 4 hydrogen. Looks good. So that is the end of this question here. And let's see if we have anything else. All right, guys. So we do have one more slide to do. And it says ozone naturally decomposes to oxygen by the reaction. 2O3 decomposes to form 3 molecules of O2 gas. The experimentally observed rate law for this chemical reaction is the rate is equal to the rate constant K times the concentration of ozones squared times the concentration of O2 to the negative first power. Show that the proposed mechanism is consistent with the experimentally observed rate law. All right, guys, let's do this one again together. So keep in mind, guys, we would want to write our rate law with respect to the slow step. So we'll say that the rate is equal to the rate constant K2, right? Since it's the second elementary step, that's why we went with K2, times the concentration of O3 times the concentration of O. Now, we need to just quickly go back and see that O is in fact our intermediate, right? Because it is first being produced, then it is being consumed. So O is the intermediate. So we obviously can't have a rate law written with an intermediate. So we have to use the pre-equilibrium approximation, right? Which is when we are going to take the rate of the forward direction. So we're going to take the rate of the forward direction and we're going to set it equal to the rate of the reverse. Again, guys, this is happening for our first step because the first step happens to have a forward chemical reaction and a reverse chemical reaction. That's why we can do this. Okay, so the rate of their forward reaction is going to be Kf1 times the concentration of O3. And then the rate of the reverse reaction, of course, is going to be the Kr1. So the rate constant of the reverse times the concentration of O2 times the concentration of O. Now, we need to write this with respect to O, right? That's what we're solving for. So the concentration of O is equal to the rate constant of the forward direction times the concentration of O3 divided by the rate constant of the reverse. So Kr1 divided by, or times O2. Okay, so now we're going to take this whole thing and plug it in for O over here. When we do that, we get the rate is equal to K2 times the concentration of O3 times Kf1 of the forward times the concentration of O3 over Kfr, so the rate of the rate constant of the reverse times the concentration of O2. Okay, guys, what I'm going to do now is I'm going to combine like terms, and we're going to say I'm going to put all the rates together as simply now just a new rate constant, right? Because if I multiply three constants together, I just get the new constant K. Then I'm going to have O3 squared because O3 is in the numerator, right? So we get O3 squared in the numerator divided by O2 in the denominator, okay? Now, if I want to write O2 and bring it into the numerator, I can do that by saying that the rate is equal to the overall rate constant times the concentration of O3 squared times O2 to the negative 1, right? So all I did is I moved this guy up to the numerator of our fraction there, and that's how I got that negative 1 exponent, and in doing so, I got my rate laws to match. And with that being said, guys, that is the end of today's video. If you have any questions, shoot me an email.